I'm glad you're all here today to learn about the idea behind high-performance HMI graphics. I'm sure you're all aware that a well-designed HMI is vital for a process plant when it comes to optimizing process, improving efficiency, and operating safely. Let's see where a high-performance graphics fit in. The HMI is the operator's window into the plant, and it's through this interface that they can control, monitor, and optimize the entire operation. It's incredibly important to get the HMI design right, as it can greatly impact the success of the entire project. The introduction of computers was a game changer for HMI design. The flexibility and ease of configuration of computers made it possible for operators to run the plant while sitting comfortably, which was a huge improvement over the methods of the past. When computers first entered the scene, they were not as powerful as they are today, and HMI design was quite different from what we're used to now. In the early days, graphics were vector-based and lacked the drag-and-drop functionality that has become the standard today. Additionally, due to the issue of screen burnout on old CRT monitors, the background of the graphics was often set to black, resulting in low-light control rooms and colored equipment and symbols on the screen. The popularity of Windows-based HMIs allowed for the concept of symbol libraries and drag-and-drop ease of graphics development, which was a huge step forward for HMI design. With the ease of developing graphics, people were so excited that they went overboard with using every color in the palette, 3D shapes, and crazy animations. However, it didn't take long for people to realize that while these graphics may have looked visually pleasing, they were not very effective in helping operators control and monitor the plant. To encourage effective graphics, the ASM Consortium, or Abnormal Situation Management, came up with the concept of grayscale graphics. When designed properly, these grayscale graphics proved to be more effective than the embellished graphics that were popular before. The idea behind grayscale graphics is that colors are only used for alarms or abnormal conditions, allowing the operator to quickly identify any potential issues. The human eye doesn't see things solely in black and white, and we are naturally drawn to colors. Research has shown that people first notice objects in their environment that have color contrast with their background. This inherent tendency to notice color may have given humans a survival advantage in the past. ASM graphics leverage this human tendency to draw attention to abnormalities. The principles dictate that no color signifies good news. In other words, any color displayed on the graphics indicates an issue that requires attention. This enables the operator to swiftly identify potential problems and take prompt action to resolve them. While ASM graphics have provided a strong foundation, the future of HMI graphics is likely to embrace high-performance graphics. These graphics build upon the concepts introduced by ASM graphics. High-performance graphics follow a set of guiding principles that have been demonstrated to enhance operator effectiveness. Unlike ASM graphics, which primarily utilize color to highlight abnormalities, high-performance graphics employ color in a thoughtful and consistent manner to convey crucial information to the operator. In this brief video, we will cover a few key aspects of high-performance graphics. For more comprehensive information, please refer to the resources provided at the end of this video. The main concept of high-performance graphics is that in HMI graphics, we present a substantial amount of data to the operator. However, unless the operator possesses years of experience or extensive training, the data alone does not provide a comprehensive understanding of how things are functioning. We require insights derived from the various values, symbols, and measurements presented to the operator in order to gain a holistic view of the system's performance. To illustrate this concept, we can draw an example from the field of medicine. Let's say your doctor ordered a blood test for you, and when you visit them to find out the result, they inform you that your fasting blood sugar level is 5.1 millimole per liter. At this point, this data may be meaningless to you. Your first question would likely be whether this value is high, low, or within the normal range. If the doctor reassures you that it is within the normal range, you may feel relieved, but you still haven't obtained a complete picture of the situation. It would be significantly more helpful if the doctor could provide you with the normal range for these values and indicate where your result falls within that range. For example, if they could inform you that the normal range for fasting blood sugar is 4 to 7 millimole per liter, and your result is 5.1 millimole per liter, it would give you a better understanding of your blood sugar level. Let's consider a scenario where someone's blood sugar level is 6.9 millimole per liter, which is very close to the upper boundary of the normal range. In such a situation, this information would raise awareness that there may be a potential issue or cause for concern. Additionally, if the person has undergone this test over a period of time and has historical data available, comparing their current result to previous results could provide further insights. Observing whether there is a consistent pattern of increasing values or a sustained elevation can indicate the need for preventive action. One of the concepts of high-performance graphics is that it goes beyond simply displaying a value, such as bearing vibration, to the operator. It emphasizes the importance of presenting not only the value itself, but also the normal range associated with that value. This allows the operator to quickly assess where the value falls within the normal range. Furthermore, high-performance graphics prioritize visual representation of this information. For instance, instead of solely displaying the numerical value, it utilizes visual elements to convey the status effectively. In the case of bearing vibration, a small analog bar can be used to represent the value. As the value increases, the analog bar can visually indicate an alarm condition, and if it further rises, it can show a trip condition. Based on these concepts, in high-performance graphics, it is indeed desirable to present analog values using an analog indicator format. In a traditional HMI, a vessel level is typically displayed using a bar graph and indication. However, this representation alone does not provide a complete picture at a glance. Operators may need to determine if the level is steady, rising, or if there is an optimum range to target. In high-performance graphics, this information is presented using a live trend and an analog indicator, which offers several interesting features. Firstly, the live trend graph displays the level over time, allowing operators to observe its behavior. Additionally, an analog indicator is utilized, which incorporates various visual elements. The desired range for the level is depicted in light blue, enabling operators to quickly identify if the value is within the target range. If the value falls into the alarm region, it is indicated accordingly. A black bar tracks the level value for a specified period, such as the past 20 minutes, providing a sense of historical tracking. The white region indicates that the level, while not alarming, is not desirable either. Lastly, the alarm and trip ranges are clearly displayed. Through a simple glance, the operator gains real insights into the level trend, the normal and alarm ranges, and can promptly assess the situation. This comprehensive visualization facilitates faster decision-making and enhances situational awareness for effective monitoring and control. In this vessel, the temperature at various stages is displayed. In traditional graphics, it may not be immediately evident whether the heat profile of the vessel is normal or not. However, in high-performance graphics, the heat profile is represented by a line graph within acceptable ranges. If the temperature falls within the expected range and appears as a blue line, it indicates that everything is functioning as desired. On the other hand, if a certain temperature is outside the acceptable range, it will be represented as an orange line, indicating a deviation from the expected values. In traditional HMI, only experienced operators familiar with the specific vessel could accurately assess the heat profile. However, in high-performance graphics, the heat profile is readily apparent to anyone simply by looking at the visualization. This approach enhances situational awareness, as the graphical representation clearly conveys the status of the temperature at different stages of the vessel. Operators can readily identify any deviations from the normal range, facilitating early detection of any potential issues and enabling timely corrective actions.